Prof and welcome to Chemistry Matters. And today we are going to do some equilibrium calculations, and we are going to introduce you to the concept of concentration tables, otherwise known as ICE tables. Okay, so let's, without further ado, kick off and look at this particular equilibrium. We've got phosphorus trichloride, and to that we are adding chlorine as a gas, and it is going to be in equilibrium with phosphorus pentachloride, which also is a gas. So that's the equilibrium we're going to be exploring, and what we are going to do is to say, right, we are going to take 0.2 moles of PCl₃, and we're going to take 0.1 mole of Cl2, and we're going to put them in a 1 litre, well, 1.00, we should say, significant figures, litre container. Okay, so we're going to mix these guys in this 1 litre container, and then we let it come to equilibrium, and when it comes to equilibrium, at equilibrium, EQBM, we find in the container there is 0.120 mole of PCl₃ remaining. So the question we're going to answer is, what is Kc? What is the value of Kc for this equilibrium at this particular temperature? Okay, so you can see there's a bit of stoichiometry obviously going on here. We've got a certain number of moles of this, a certain number of moles of this. But how then do we go about solving this problem? Because all that we know basically is the starting amounts of these guys and the finishing amount of PCl₃. And that doesn't seem to be enough information for us to actually solve this equation, because we don't know anything about the amount of PCl₅. And that's going to be kind of important, you would imagine, to know that in order to calculate Kc. So, how do we do this? Well, if we're calculating Kc, then there are three things that we need to know. We need to know the equilibrium concentration of PCl₃, we need to know the equilibrium concentration of Cl2, and we need to know the equilibrium concentration of PCl₅. So, this is where the concept of the concentration table comes into play. Now, there's more than one way of solving these types of equation, but again, I'm just showing you this, and you know, if you've been taught a different way and you still get the right answer, that's all fine. But let's set up a concentration table for this particular system. So we start off with the initial, and the change, and the equilibrium concentrations. Okay, so let's draw a little grid, like so. Okay, here's our little grid. And you can see that on our grid we've got 1, 2, 3, 4, 5, 6, 7, 8, 9 rectangles, squares, call them what you will, that we want to fill in. Because what we want are these three here. These are going to be the equilibrium concentration of this, equilibrium concentration of that, equilibrium concentration of that. And we need those in order to calculate K. So let's fill in what we know. What did we get told in the question? And again, this is always the same when you're answering questions in a chemistry exam or whatever. It's always a really good idea to write down the information that you have been given. Okay, so what have we been told? We've been told, right, first up, we've got a 1 litre container. So that makes things easy because the volume is 1, so we're going to be dividing by 1 to turn into concentrations. That makes life easy, okay? We're told that we had initially 0.2 moles of PCl₃ in a 1 litre container, so the initial concentration of that is going to be 0.200. Now, likewise, we were told that we mixed it with 0.100 moles of chlorine in that 1 litre container, so the initial concentration of chlorine was 0.100. And the other thing that we were told was that finally, after the whole system had come to equilibrium, we had 0.120 moles of PCl₃ left. Okay. So we've got to fill up all of those slots somehow. Those are the three pieces of information we've been given. What now can we get out of those pieces of data? Well, the first thing is we can say, right, the initial concentration of PCl₅ must be 0. Because at the instant that we mix these two, we've got precisely none of that. Okay, so the initial concentration of that is 0. Now, we've still got to somehow fill up these slots to get these two things here. How do we go about doing that? Well, here's the piece of information that's vital. Because it's saying we start off with 0.2 mole per litre of PCl₃, we finish at equilibrium with 0.12 mole per litre of PCl₃, which means that the concentration of PCl₃ has changed by minus 0.08. And that one piece of information now allows us to fill in the rest of the table. Okay? Now we come back to stoichiometry. I keep telling you, you can never do too much stoichiometry. The mole ratio for reaction of PCl₃ and Cl2 is 1:1. So if the concentration of PCl₃ changes by minus 0.08, then the concentration of Cl2 must also change by minus 0.08. Must decrease by minus 0.08. And therefore, PCl₅, again, the mole ratio between PCl₃, Cl2, and PCl₅ is 1:1. So if the concentration of this is decreased by that much, then the concentration of that must have increased by that much. And now we can get these guys here. These are what we want, these values. How do we get them? We simply add up these squares. Okay, so you add up these slots, 0.1, okay, plus minus 0.08 is equal to 0.02. Okay, let's put an extra significant figure on there just to keep everybody happy. Okay, and then we add up these guys to get this slot here. 0 plus 0.08 equals 0.08. Okay, and now we've filled up all of the slots, and importantly, we've filled up the ones that we need to calculate Kc. Okay, those are the slots that we need to calculate our value of Kc. So where do we go from here? Well, we use these values now in our expression for Kc. So we write our expression for Kc and plug in those values. Okay, so let's do that. Those are the equilibrium values. Let's write our expression for Kc, keeping those values there. So the expression for Kc is equal to the concentration of PCl₅ over concentration of PCl₃ multiplied by the concentration of Cl2. Plugging in these values, PCl₅ concentration is equal to 0.080 over PCl₃, we said was 0.120, and the concentration of Cl2, 0.020. And if we do that calculation, we end up with the value 33.3. Okay? And that is our value now for Kc for this particular equilibrium under these particular conditions. Okay? What does that tell us? A value of Kc that's greater than 1. That says that products are going to be favoured at equilibrium. It's not too different from 1. So we would expect that we'd have a slight excess maybe of PCl₅ at equilibrium in this case, when we get to equilibrium. And you can see how stoichiometry is all important here. That using the concentration table, we have to use the stoichiometry of the reaction in order to get these equilibrium values down the bottom. Remember, these are the ones that we need in order to fill in our Kc expression and solve the equation. Okay? So that is one example of using a concentration table. That's a fairly straightforwardish example. I hesitate to use that word, but it is a fairly straightforwardish example of how to use a concentration table. Next time we will have a look at a slightly more advanced example using, again, the same concepts, the same ideas, but I hate to say it, the maths is going to be a little bit more complicated. Okay? So until that time, stay safe and we will see you in the next video.